Hi, Rajneesh Kumar this side. Welcome back to my channel. So, in today's lecture, we are going to understand what exactly is DFS. Then it is followed by components in DFS, matlab how to count all the components using DFS, right? And which is again followed by if we have left with some time, then the next problem will be the hash path. Hash path basically uh, total or is there any path exists in between the two vertices, right? So let's start with DFS. What exactly is DFS? DFS is depth first search. What exactly mean is depth first search? So if I start from any point, suppose this is the entry point. Suppose there's a graph which have lots of branches. So again branch, again branch, again branch, again branch. Right. So depth basically I start from any entry point, I keep on moving on that particular stem or that particular branch, or it's a stem, right? On the particular stem, and at this point there's a two path, I have a two path to go. So there is a branching, so I move to the first branch and I keep on moving till I find the endpoint. As soon as I found the endpoint, I will backtrack to that stem till that diversion point and move to the another branch. I keep on moving. Again, there is a two diversion, so I move to the first diversion. I keep on moving until I find the endpoint, and again I backtrack, move to another branch, and again backtrack, move to another branch, backtrack till the source. Now source have a two branches, right? So I already traveled the first branch in entire depth. That's why it is known as a depth first search. So I already search the element, or I already search whatever you want me to search in that branch. Now I'm free to move to other branch for this search. So I start moving on the other branch. So there is again two branches. I keep on moving, again backtrack, again keep on moving, again another branch, backtrack, keep on moving, backtrack, keep on moving, backtrack. So this is known as a depth first. That is why this is known as a depth first search. Now how we should apply depth first search, because it is a kind of recursion. If you remember the recursion, in recursion we exactly do the same thing, right? So how it is different from the recursion? So in recursion usually we don't care about the cycle. So graph has a very important concept of cycle, and it's a very basic problem in graph. So what exactly is cycle? Suppose there's a two vertices A and B, and there is a bidirectional connection, A to B and B to A and C. Now A will move to B. From A point I will move to B, and from B point, because I have an option to move back to A, I will move to A. Again A to B, B to A, again A to B and B to, and it keep on moving till infinity, right? It keep on repeating till infinity, and it never going to be stop. So by using this algorithm, I will not able to traverse the C point. So this is the very basic problem in graph. So how to prevent this that particular bug or that particular problem? To prevent this problem, we use visited. What is the concept of visited? So visited say mark that vertex that you already visited. How should I mark that vertex? How will keep track of that vertex which I already visited? To track that vertex, we will use maybe a hash set, because there's only vertices. So that's why I'm using a hash set, or I can use a visited array. Why visited array? In which scenario we should use hash set? In which scenario we should use visited array? Visited array means if the vertex are in some kind of sequence or some kind of arrangement. If you see in my graph, there is a arrangement, like it's a sequence 1 2 3 4 5 6 7. It's a sequence, it can be represented. These vertices can be represented as an index of an array. So in this case I can use a visited array. But imagine a graph in which vertices are like 100 or 200 or 368 or 490 or 699. In that kind of graph in which vertices are in some kind of random order, I will use hash set. Okay, so now you have a now you know the difference between when should we use a hash set or when should we have to use visited array. So what is the definition, not definition, what is the pseudo code of DFS? So DFS say, because we have to use a visited array concept, DFS say first mark the source, mark source, and then traverse my all unvisited neighbors for all unvisited, not visited one, all unvisited neighbors, for all unvisited neighbors, not neighbors, just neighbor, because I use for all unvisited neighbors, call DFS for neighbor. So that three line of code is known as a DFS. That three line of code is known as a DFS. That is a pseudo code. Let's write that pseudo code in the form of code and then make a quick dry run. Because I have to use a visited array here and the sequence are in some kind of order, so I can use a visited array, right? So visited array can be used. So let's make a visited array 0, 1, 2, 3, 4, 5, 6, and 7. 0, 1, 2, 3, 4, 5, 6, 7. So here each vertex can be treated as an index of that array, and that visited array is of boolean. So I will make a function. After doing this, we will analyze the time complexity of that DFS, and then we move to the components, all components of a graph. So before moving it, let's focus on DFS. Array list. Then I required a boolean visited array, not b visited array, and of course source. So our pseudocode say mark source as true, and then for all unvisited neighbors, for all unvisited neighbors means my neighbors are, if you remember the urgency list that I represent in my previous videos, that for example vertex 4 have edges 1 comma 10 and 5 comma 2 and 3 comma 40. So vertices are, so edges are 4 to 1, 4 to 5, and 4 to 3, right? And this adjacency list contain 3 edges. That's why I can make a loop for all edges in that vertex. Let's make a DFS call. Before making a DFS call, please make sure that that vertex is unvisited. So visited of e dot v should be false. If that vertex is false, make a DFS call there. Make a DFS call there. TP visited array and e dot v. Cool. So that function is sufficient for the DFS call, and let's count. Let's make it return type int. Why I'm making return type int? I will tell you. The count is equal to 1 because of that particular source, because source can be counted as a one vertex, right? And count plus equal to DFS, and here I will return count. So what exactly the DFS function expected to return? So that DFS function will return all the vertices that are present in that graph. So in this graph, it contain total 7 vertices. So that DFS, when I make a DFS call on that graph, that function will return me 8, and that traverse all the vertices. So this will get me some kind of verification that my DFS call is able to reach each and every vertex of the graph. How it will going to reach and every vertex of the graph? Let's check out in a quick dry run. This is my code. This is my code, and here I am with vertex with starting point is 1. So as a starting point is 1, the count here, count is also 1, count is 1. Mark it true and move to all neighbors. So my all neighbors are 2 and 4. As soon as I visit 2, I will mark it true, count is still 1, count is still 1, and I will move to my neighbors 1 and 3. So I will try to make a recursive call at 1, but 1 is already visited, so I will not make any recursive call there, and I try to make a recursive call, not recursive call, it's a DFS call. So I will try to make a DFS call at vertex 3, but vertex 3 is unvisited, so I will make a DFS call there, mark it true, and at vertex 3 count is still 1. Then I will make a again DFS call, try to make a DFS call at vertex 2 and vertex 4, but you find that vertex 2 is already visited, so I will not make any DFS call. 4 is unvisited, so I will make a DFS call, of course, there before making a DFS call. So I already make a DFS call there. After making DFS call, I will mark true that visited array, count is still 1 there, and I will make a 3, try to make a 3 recursive or DFS call, sorry. I again keep saying recursive. It's not recursive, it's DFS, because DFS and recursion both are exactly same. It's just the same thing. So at 4, I try to make a DFS call at 1, but 1 is already visited. Then I try to make a DFS call because 4 has 3 neighbors, 1, 3, and 5. Then I try to make a DFS call at vertex 3, but 3 is already visited. Then I try to make a DFS call at 5, but 5 is unvisited. So I will make a DFS call at 5, mark it true, and move to vertex 6 and 7. So at, of course, at 4 also, but 4 is already visited, can't do anything. 6 is unvisited, mark it true, count is still 1, and 6 will make a DFS call at 7. 6 will make a DFS call at 5 and 7. But as you see, 5 is already visited. Because 5 is already visited, I'm not able to make any DFS call there. Then I move to 7. 7 is unvisited, mark it true, and 7 will try to make some DFS call at 6 and 5, but we find that 6 and 5 both are visited, so 7 will not make any DFS call there. So the for loop will keep running for the 2 times, but that if function block that DFS call, and we return count 1 there. So the one count 1 is written by there, right? And at vertex 6 count is already 1, so 1 plus 1 become 2. So at vertex 6 count become 2. Now for loop will run for the 7, but 7 is already visited in my visited array, it will not make any recursive call. Then I return count 2 from this state, from 6 the count return 2. At 5, because I receive count 2, so I try to add that count 2 to 1, it become 3, so I will return 3 here. Now 3 will add up to 1, it become 4, 4 will add up to that 1, it become 5, 5 will add up to 1, it becomes 6, 6 will add up to 1, it becomes 7. So if you notice that I traverse each and every vertex only single time, right? So, or either I say I traversed all edges, right? Because 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So I try to traverse each and every edges, but only those edges are in my list which is unvisited, and the count is 7. So a DFS call, so that function of DFS call, because it traverses all the edges, that's why the complexity of that function is O of E, not V. O of E. Why not V? Because if there is some other vertices, right, 8, 9, 10, which is not connected to my graph, my DFS is not able to reach those vertices, right? So my DFS is only reachable to only that vertex in which for which the entry point is given. So entry point of 1 is given, so from one entry point I'm able to reach only those vertices which is reachable by entry point 1. Like can I reach to 7? Yes, because 7 is reachable by 1 by path 1 to 4, 4 to 5, 5 to 7. Yes, it is reachable. That's why I can traverse till 7, but I can't traverse at 8 because there is a no connection in between that graph to 8. There's no connection exist. That's why the complexity is total number of edges that exist in that graph. So this is the simple DFS call. Now let's move to all components. What exactly is the all components? If we talk about the components, if we talk about components, uh, imagine there is a one more graph, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So there's a now this is a complete graph. So how many components are there? One. This is a one component. 2, 3, 4, and 5. So there's total 5 components that are exist in the graph. These 5 components are not able to reach by each and every graph, right? Each and every component, because this component is not reachable by this graph, this graph, this graph, or this graph, because there's no connection exists in between this graph. So that's a very standard problem of count islands. So count islands is a completely similar kind of problem. We will solve that problem after solving this, of course. So I will make a complete DFS section in which I pick DFS related question, only DFS related question, and try to solve it. So I pick it from Lead Code or maybe Introbit or maybe some other website, maybe Geeks for Geeks, and I solved it in that same folder. Okay, you will get to know. Cool. And now think of it, my function of DFS, is able to traverse the entire component that is connected by somehow directly or indirectly is connected. I able to traverse the each and every vertex, but I'm not able to traverse this vertex. To traverse this graph, I need a entry point. What kind of entry point? Any entry point will work because it's a bidirectional graph. 9 will work as an entry point, 8 will work as an entry point, 10 will work as an entry point, any component will work as an entry point. Maybe you can also say that is 8, that is 10, that will also work as an entry point. So I will make a big uh, visited array. So for the visited array, I will just writing indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's move to 1. By traversing at 1, if I make a recursive call, so 1 will move to 2, and 2 will move to 3, 3 will move to 4, 4 will move to 5, 5 will move to 6, 6 will move to 7. So 1, 2, 3, 4, 5, 6, 7, that all are visited, right? And there's no other connection, that no other branch that exist. It will not make any other recursive call. Then I start picking every vertex as an entry point. Can I pick 2 as an entry point? No, because 2 is already visited. It means 2 is a part of a component which is already get visited. Can I pick 3 as an entry point? No, because it is already visited. So it is a part of some component which is get already visited or which is already traversed in my previous DFS call. Can I pick 4 as an entry point? No. Can I pick 5 as an entry point? No, because it is already visited in my some other previous DFS call. Can I pick 6 as a DFS call? No. Can I pick 7? Sorry. Can I pick 6 as a source point? No. Can I pick 7 as a source point? No. Can I pick 8 as a source point? Yes. I can pick 8 as a source point because 8 is still unvisited. It means that my previous DFS call is not able to reach at vertex 8. So in this scenario, I will pick 8 as an entry point, mark it true, and traverse to, and I will traverse to 11, or I will traverse to 12. So now I mark 11 as a visited, because now I'm at 11, so I will mark 11 as visited vertex. Now 11 have option to call 8, but 8 is already visited and there's no other neighbor, so I will backtrack from that point. Now I will go to vertex 12. 12 is also get visited, but 12 doesn't have any other neighbor, any other unvisited neighbor, because 12 have a neighbor 8, but 8 is already visited, so 12 doesn't have any neighbor. If suppose there's a line also, then 11 is already also visited, so it's not no. If there is a line, then 11 will make a call to 12, so just remove that line for the sake of the simplicity. Now I backtrack from 12, then I will make a third recursive call, third DFS call to 10. I will mark 10 as visited. 10 will make recursive call or DFS call to 9. I keep on saying recursive. So you can assume that recursion and DFS both are the same thing. So at 9, at vertex 9, because 9 is unvisited, I mark it visited, and 9 doesn't have any unvisited neighbor. So I will backtrack from 9, backtrack to 10. 10 doesn't have any other branch. So I backtrack to 8. 8 doesn't have any branch, and all vertices get visited. So this component is also get visited. Now, can I pick 9 as a 9 as my source point? Okay, just don't forget to increase your count of components. Initially, the component is 1 because I visited that component. Now I make a fresh DFS call to for this component, so count will become to 2. Now I'm trying to make another DFS call. If I found any another source point, can I pick 9 as a source point? No. Can I pick 10 as a source point? No, because 10 is the part of some previous DFS call, so that's why it is visited. Can I pick 11 as a visited source point? No. Can I pick 12 as a source point? No. Can I pick 13 as a source point? Yes, because it going to be a fresh DFS call. Increase the count of component to 3. Now make a DFS call for 13. 13 will call to 14. Both get marked, and I backtracked it. Can I pick 14 as a source point? No, because it is a part of some previous DFS call. So I will move to the 15. So as soon as I move to 15, and 15 doesn't have any neighbor, 15 doesn't have any neighbor because it's a fresh recursive call, I will backtrack it. Can I pick 16 as a source point? Yes, 16 can be treated as a fresh source point. So increase your count to 5. Mark 16. 16 will call to 17. 17 is now my the new source. 17 will try to make some DFS call to their neighbors, but there are no neighbors which is unvisited. So I will backtrack from 17 to 16 and backtrack from 16 to my base. Now 17 is already visited and there is no other vertex. So if you remember, in this scenario, I traverse the all possible edges of, if there is a total E1 edges, in this there is E2 edges, in this E3 edges, E4 edges, and E5 edges. So in my first DFS call, I traverse entire E1. In my second DFS call, I traverse entire E2. In my third DFS call, I traverse entire E3, because total E3 edges exist in this component. In this component, there E4 edges exist, and in another, there E5 edges exist. The summation of all the edges will equivalent to E, can be treated as all edges that are exist in the graph. But if you noticed, that component contain only single vertex, so it is highly possible there is some other graph which contain 18, 19, 20 till 10 is to power 3 without any other edge. So this is all the vertex, and my for loop will keep on moving, will keep on traversing these vertices. So that vertex effect will contribute in my time complexity. So the complexity will become E because of all the edges, and V because of that single component, because I traverse that visited array, right? That's why. So the complexity will become E plus V. So the traverse the all components in a graph, the complexity is E plus V. But just to travel a single connected graph, if I make a DFS call on a single connected graph, the complexity will be O of E. Let's code it. Public static int all components. So for the all components, I just need visited array. If I have visited array, I will make a count for components equal to 0. I will traverse on my visited array, or as soon as I figure out any unvisited index, I treat that index as my source point, equal to 1, because 0 is not a vertex in our graph. So I start my component, I start my graph from index 1 and traverse till visited dot length, visited dot length, and I plus plus. If that vertex is unvisited, then I will increase component count by 1 and make a fresh DFS call for that index by treating that index as a source point and pass that visited array. Now return that components, total components. Now if you notice that my DFS function return a count value, that count value represent number of vertices that are exist in that component. So by that information, number of vertex, I can able to print that information also. uh, like component plus, let's print the value of component, let's make it number of component, number of component plus total vertex or total population of that component. So the population is a correct word, or you can say that a vertex. So total vertex or population will be number of vertex. So that all component will able to traverse the entire graph, whether it is connected, whether it is not connected. If it is connected, so all the vertices it already visited. Suppose that whole graph is somehow visit connected, somehow it is connected, then my single DFS goal will traverse each and every vertex, and all the indexes of visited is already marked true. But my for loop will try to make a fresh DFS call, but it is not able to make any fresh DFS call because of that if function, because if function will prevent that extra DFS call, because all the vertices already visited. So this is how we will able to count the components in our graph. Now the one more problem that I want to solve, but not on this video, that is hash path. We will solve that problem in another video. Hash path and hash all path. After solving these two problems, we will move to the all the questions of DFS, all the question related to DFS. So we'll make a simple uh, folder in my github directory. So here I make a folder of DFS in which I solve all the DFS related problems. Then we move to BFS. So first we try to understand what exactly is BFS, uh, how to how to uh, how to code BFS. Then we move to union find. Before moving to union find, first we solve to question related to BFS. Then we move to union find. Then we solve question related to union find, uh, and then we move to some other algorithms and question related to those algorithms. I hope you like my video. If you like my video, please like, please subscribe this channel, and do let me know if you face any difficulty to understand this algorithm or understand any segment of my video in my comment box. If it's all good, then please let me know. If it is not good, then please let me know. Subscribe my channel if you just visited to my channel, or try to share as much as you can. It helped me to grow. Okay, bye bye.